Hello and welcome. We were discussing about different types of lasers, and we were discussing about helium neon laser. So we'll start from there. So on your screen you have the energy state diagram. I'm sorry about the picture quality. That's what I got. Now, so the initial excitation is achieved using electron discharge through electron impact, and the populated excited helium atom transfers the energy to the neon atom. So in that way, essentially, one is creating a population transfer as well. So thus you actually create a population inversion within the neon, the energy states of the neon atom. So this populated energy levels of neon, they lie above the lowest excited state, and as I said, a population inversion is created with respect to these states, and as a result we can have laser action there. And there are three possible laser wavelengths that can be obtained. This 632.8 nanometer, 1.152 micrometer, and 3.391 micrometer. The most common wavelength for helium neon or Hini laser is 632.8. Okay, and there are a lot of applications of this Hini lasers, and for any optical alignment, Hini laser is the one that is used. A few more things I would like to talk about here is that following emission, neon undergoes a two-step radiationless decay back down to its ground state, and this involves a transition to a metastable 2p5-3s1 level, followed by a collisional deactivation at the inner surface of the tube which contains the gas, that is the helium neon mixture. Now note this one, you have to depopulate the lowest excited state involved in the lasing action, because that will ensure that you have population inversion, right? So and this rapid decay from the lowest excited state is achieved through collisional deactivation of this excited neon atoms, and this collision that I am talking about is the collision between the excited gas molecules with the inner surface of the tube. Okay, therefore if you have to achieve efficient deactivation of this lowest excited state, which is necessary, you need to provide much more surface area compared to the volume of this container. So this container essentially is a tube, a cylinder. So what you need to do, you need to increase the surface to volume ratio, which essentially means that you reduce the diameter of this cylinder, right? So that is what it's stated here. So the tube either has to be extremely long, and also the diameter should be extremely small. And practical number would be like a couple of millimeters, 1 to 2 millimeters, the diameter I am talking about. Now the advantage of Hini laser is that we already mentioned it has a very narrow bandwidth. This Hini laser is quite small and it's inexpensive. So we will show you the actual picture of this Hini laser. So on your left there is a schematic of this Hini laser. So this white part is essentially uh, holding everything together, and inside there you have the gases, and you have the cathodes and anodes placed at different regions. So this is the aluminum cathode kept here, while the anode is right here. So due to this discharge you get laser emission, which is shown by this red color line, and you have either a plane mirror here and an output beam here. So you get an output through this one. So this is an overall geometry, and this whole tube which contains the gas must be sealed well, otherwise your laser properties will degrade in no time. Okay, so this is another view of a real tube containing Hini and this electric discharge system. So this is essentially an electric discharge tube, and all around this one you have gas moving around, okay, in a overall sealed container. And this part actually is inside so this commercial Hini laser. So this is a commercially available Hini laser. So these are really small, and they are really handy. They can be like just few inches long. Okay, so from this picture itself you will get an idea like how small it is. I mean, these are like normal screws. So with respect to that, you can easily gauge the dimension of this particular laser. So this laser is really portable, handy. You can put it in your pocket also if you can carry the power supply which gives power to this electric discharge system. And also this is quite a narrow bandwidth, and it's quite collimated also. You can achieve both polarized or depolarized light output from Hini lasers. So this is extremely useful in various applications. Now after talking about Hini, we'll talk about another atomic gas laser, or ionic gas laser rather. So we'll talk about argon laser, or very commonly called argon ion laser. So the simple the component of this laser is just one inert gas, that is argon, and this is our active medium, and the pressure that is maintained for this argon, it is also kept in a sealed container like helium neon, is 0.5 millibar, and the diameter is approximately 2 to 3 millimeter diameter of that container. And similar to Hini, here also the excitation is achieved by electric discharge. Now what is done here? First, unlike in Hini, in argon laser, the electron impact first ionizes the argon atom, and then this argon plus or argon ion is further excited. Okay, and this particular excitation it produces population of several ionic excited states, and these states are responsible for laser action. Now there are several emission wavelengths that are achieved from this argon ion laser, and however this is not a continuously tunable laser system, but over a range they can give rise to several different discrete frequencies. Okay, and this range is roughly around 350 to 530 nanometer. Okay, and there are certain emission lines which are really famous. They are like 488 nanometer and 514 nanometer, which results from a transition from the singly ionized states with electron configuration of 3s2, 3p4, 4p1 down to the 3s2, 3p4, 4s1 state. And further radiative decay to multiplet associated with the ionic ground configuration of 3s2, 3p5 then takes place. Okay. So here is the energy level diagram. So you know how it is done. So you first ionize the argon system, and then you know play with the energy levels of argon ion system, and the argon ion system have a ground state here. Okay, and you have a population inversion created here essentially. So from these states it can come down to this state here, and corresponding two lines. So whether it's coming from here or here, you get different output. So you can see that I can get either 488 or 514 nanometer laser light from these two different transitions. Few important things about this argon ion laser. This laser cycle is completed by electron capture or further impact excitation. So also several different wavelengths is produced by etalon. We mentioned it earlier in one of the earlier classes what etalon is. You can use also you know a prism to disperse them. Okay, so you know if all of the lights are coming together, then you need to use something like a you know which will act like a grating, and it will disperse the light so that you can you know utilize different wavelengths for your work. Now one can select a single longitudinal mode, and by that you can achieve extreme narrow line width as small as 0.0001 centimeter inverse. You know you can figure out taking 488 nanometer as the central wavelength of the emission line, and using this value of 0.0001 centimeter inverse full width half maxima, you can see you can exactly calculate what is the range of wavelength, okay, that one single line you know corresponds to. So what I essentially mean that if I draw this laser line like this, so this width corresponds to 0.0001 centimeter inverse. Central line, it corresponds to 488 nanometers say. Then what is this wavelength in terms of nanometer here and also here? You will see they will vary in third or fourth decimal. So it's literally really narrow band like. Now this is advantage. What disadvantage we get here in case of argon ion laser? It requires you know large and continuous flow of energy. Okay, because you have to maintain the population inversion there continuously. So you need to pump it really hard. You can get a quite decent you know power from argon ion lasers. It can range from few milliwatts to few watts, like you know 20-25 watts. Now we have seen in case of Hini laser, they are like very handy. They are you know good quality laser beam. They are comparatively quite cheap. You hardly have any kind of maintenance. On the other hand, these argon ion lasers are extremely expensive compared to Hini. It is little difficult to maintain. In that way, it is little fragile. But in spite of these disadvantages, this argon ion laser is widely used, particularly in the field of spectroscopy, because of its extreme narrow, line width, spectral line width. Particularly in case of Raman spectroscopy, this is very commonly used. Next, we will go through real quick this copper vapor laser system. This is another atomic gas laser. So this copper vapor laser is essentially a 3-level system, and like any other gas laser, here also the electron impact plays a role. So the electron impact on the ground state copper atoms results in the excitation to 2p state, which belongs to the electron configuration of 3d10-4p1, and from this state the transition to a low-lying 3d9-4s2 state, which has this symbol 2d, can take place, and the corresponding laser emission is achieved at 510.5 and 578.2. In this case also the de-excitation takes place due to the collision of the excited gas molecules with the wall of the tube which contains these gases. And this copper vapor laser, it operates in pulse mode with repetition rate of about 5 kilohertz. So it's quite high rate laser. How you design this laser? So the physical design, it involves an alumina plasma tube containing small bits of some flecks of metallic copper, and this tube also contains low pressure of neon gas, which is approximately kept at nearly 5 millibar, which helps to sustain the electrical discharge. So now the basic advantage of copper vapor laser is that it emits a very high power of visible laser light. So this is used in various metallurgical applications, okay, because it uses visible light and having very high power. Okay, now let's move on to other type of gas laser which contains molecules. So far we have used, say, like helium and neon. So helium neon is not a molecular gas laser, right? Because helium is an inert gas, neon is an inert gas. They do not react, do not form a molecule. So they are individual atoms just mixed together. Argon, copper vapor, they are individual atoms or ions. Okay. So now we will consider certain gas laser system which uses small molecules as active medium. So one of them is a carbon dioxide laser, and here, so mostly we can talk about the electronic energy levels which involves in laser action. Here even the vibration and rotation levels are involved in laser action. Okay, so this is something which you should note. The lasing medium consists a mixture of carbon dioxide, nitrogen and helium gas in varying proportions. Okay, we will see what other molecules or atoms do here. Now this picture shows you the basic design of this laser. So like any other gas laser, you also have a sealed tube here, and you provide the electron impact by putting some electrodes accordingly, and at a given voltage difference you create electric discharge, excite the gas molecules, and ultimately get the emission and hence the laser. So you have this helium, neon and carbon dioxide gas all mixed up here, okay, and you put an end mirror here and output coupler here, and ultimately you get the laser output. Quite simple design. And this is another design here I shown. Reason is that this laser also needs to be cooled down. So it is cooled down by supplying water. Okay, so this water goes in through this inlet, and then water goes out from this outlet, correct? And there is like a sheath of water all around, and it continuously cools down this whole system comprising of electric discharge and this gas cylinder. This is required like other solid state lasers that we discussed earlier. Okay, so this is the energy level diagram of carbon dioxide, and it shows how the lasing takes place here and what are the levels which are involved, what are the rho vibrational level that are involved in this lasing action. Now here again you see different types of nomenclature for the states. Okay, so these are particularly used for rho vibrational levels, and unfortunately we will not be able to discuss about this particular type of nomenclature, how these term symbols are formed. Anyone interested, you can look at a standard spectroscopy book or standard quantum mechanics book. You can find how to get this particular symbols. Okay, so right now you just take them at different rho vibrational states corresponding to different electronic states. So what we have here for this energy level diagram. So first, of course, you give the electron discharge. So electron impact will take the molecule from the ground to the excited state of nitrogen molecule. Okay, so the first electron impact takes place in the nitrogen molecular states, and then this excited nitrogen electronic state and the corresponding vibrational and rotational state transfer their energy and hence the population to the levels of carbon dioxide molecule. Okay, because this rotational sublevels belonging to vibrationally excited states are populated by this electron by this collision. So ultimately what happens, these states where the population is being transferred, so this is essentially you are doing the population transfer, right, by transferring the energy. Now this state where it is coming is a metastable state. So because it is a metastable state, so after every excitation and following collision, the number of carbon dioxide molecule in this excited state is increasing, and then it can come down to the low lying energy states, and these low lying energy states like here or here, they undergo very rapid relaxation to the to ultimately to the ground state. Thereby you can achieve sufficient population inversion, and hence you can get the laser action. So the laser action gives you this 9.6 micron and 10.6 micron, two different lines, and you can see these are in infrared, and certainly it involves the vibrational levels. Okay, so we have already discussed this. So one more information here, that a small carbon dioxide laser with a discharge tube about half a meter in length may have an efficiency rating as high as 30%, and it produces a continuous output of 20 watt. So a continuous wave laser having a 20 watt energy is amazing. This can be used for welding, or cutting metals and all those things. So in metallurgy it finds tremendous applications. If you get access to a good machine shop or workshop, you will see that many places these carbon dioxide lasers are used to do a lot of machining and micro machining. So the last laser in this particular section we will discuss about is nitrogen laser. And nitrogen laser, the principle is very much similar to carbon dioxide, with certain differences. What are those differences? The electronic states are involved in case of nitrogen, and the states, the transition occurs between 3 pi u to 3 pi g. The upper level, that is 3 pi u, has a lifetime of 40 nanosecond and hence cannot sustain population inversion. All the excited nitrogen molecules undergo radiative decay together to give super radiant emission, and short pulses, around 10 nanosecond pulses of wavelength 337.1 with a bandwidth of 0.1 nanometer is generated, and the repetition rate that is obtained from this nitrogen laser can be varied between 1 to 200 hertz. Okay, so you can see here that the differences here is like in the near UV region we have the output from nitrogen lasers, and otherwise this all these gas lasers has very similar kind of configuration. Okay. So next we will talk about a totally different types of laser, which is chemical laser. So from the name itself you can understand that there are certain chemical reaction takes place which provides the systems that give rise to levels or energy states that ultimately can give us laser action. So under chemical lasers we will look at two particular type of systems. One is iodine laser, and second thing is called an excitement laser. So in the following class we will talk about these two laser systems in quite detail. Thank you very much.